The first question says, the white solids, sodium sulfate and potassium carbonate, may be distinguished using a flame test. Identify a material from which the flame test wire could be made and justify your answer. Okay, Alishba?
Nichrome wire.
Excellent, from nichrome wire. Or we can say platinum, but of course we know that platinum is expensive. That's why we prefer the nichrome wire. Yes,
Yeah, and use
justify
it
your
because
answer.
it's unreactive with
Yes.
other metals.
Yes, excellent. It's inert, or it does not react with metals, or it does not form a flame color with the flame. Yes, excellent, Alishba. Okay, describe how to carry out a flame test on a solid, giving the expected flame color for each of these compounds. Abdurrahman?
So first we will dip the nichrome wire in HCl.
Yes, excellent.
Then place a small piece of the metal to be tested on the nichrome wire.
Yes, excellent.
Then place the wire with the metal on it in a Bunsen burner flame.
Yes.
The sodium will have yellow flame and potassium will have lilac flame.
Yes, excellent. So here we say that as excellent, Ya Abdurrahman. Hello, Ya Omar. So we say that at the beginning we have to dip the nichrome wire in HCl. And we also, after we dip it in HCl, then we dip it in the solid to place a part of the solid on the loop of the nichrome wire, and then we are going to place the nichrome wire in the Bunsen flame. Okay, and we will see that sodium would produce a yellow color in the flame test. They said, describe how to carry out a flame test on a solid, giving the expected flame color for each of these compounds. So here we have sodium. They said sodium sulfate. So we have sodium. The sodium will give a yellow-orange color, and the potassium will give a lilac color. Okay. Sometimes they will ask you, why do we place HCl? Why do we sometimes here, instead of saying after we dip the nichrome wire in HCl, sometimes we add drops of HCl on the solid, and then we take part of the solid containing, of course, the HCl on the loop of the nichrome wire. So sometimes they will ask you, why do we use HCl and not any other acid? Why do we use the HCl and not any other acid? So here, do you know the answer here? Asma, do you know why do we use HCl and not any other acid?
No.
Okay. Yes, excellent, Abdurrahman, bravo. No, Rudaina, as Abdurrahman said, because this question usually come in exams. Why do we use HCl when we place drops of HCl on the solid and take it on the nichrome wire? This usually come in exams. So why do we use HCl? As we said before, and as Abdurrahman is saying now, that metal chlorides are more volatile. Metal chlorides are more volatile than others, than other metal salts, You have to know this because it comes a lot in exams. Why do we place drops of HCl on the solid and then we place part of it on the loop of the nichrome wire? This is because the metal chlorides, don't say HCl is more volatile, because sometimes you say that. Sometimes students are confused and they say that HCl is more volatile than the other acids. No, it's the metal chlorides that are more volatile than the other metal salts. It means that if you put sulfuric acid, then you will get metal sulfate. If you put nitric acid, you will get metal nitrates. But metal chlorides are more volatile. So when you place them in the flame, then they are volatile and they produce the colors corresponding to their metals. Okay. Let's see, excellent, Abdurrahman. Let's see number B. which paper is this? I think it's Jan 2021. I think, yes, it's Jan 2021. Type. Okay, here sodium sulfate and potassium carbonate may also be distinguished during using chemical tests. Give a chemical test for each compound, which would confirm the identity of the anion. Now we want to confirm the identity of the carbonate and of the sulfate and include the expected result. Asma?
For the carbonate, we'll add the hydrochloric acid, and there
Yes.
would be an bubbling of CO2 gas, and
Yes.
CO2 gas turns lime water milky.
Yes, so here we say
And-
add HCl, effervescence or bubbles, effervescence or bubbles of a colorless gas, that turns lime water milky, okay. And sometimes also in many exams they will tell you how to write the equation of this reaction. How does the lime water turns milky? Then we say that if they want, because here they don't ask us, they didn't ask us about this, but sometimes they will ask you to write the equation between the acid first and the carbon dioxide, and the carbonate in the salt. It produces carbon dioxide and water. So this is the first equation. The second equation, that when carbon dioxide reacts with lime water, which is the calcium hydroxide, it produces calcium carbonate. This is the solid that turns lime water milky. It is the calcium carbonate solid plus water also, plus H2O. Okay, so sometimes they will ask you to write these equations, so you have to know how to write them. But of course, in this question, they didn't ask this. They only said, give a chemical test. So as Asma said, add HCl, effervescence or bubbles of a colorless gas that turns lime water milky. Excellent. What is the other chemical test, Asma?
Okay, we will add the barium chloride followed by
Excellent.
hydrochloric acid.
No,
And there is
it should be the acid before the barium chloride. You should add. Okay, so here we add an acid, then barium chloride. We said because we want to get rid of any. No, here we don't have. Here we can. Here you can add the barium chloride and hydrochloric acid. Whether this is this before that. Yes, and what happens? Yes, ma'am.
white precipitate forms.
Yes, excellent. A white precipitate of course, you don't have to say of, but I'm just reminding you of barium sulfate. It's a white precipitate of barium sulfate forms. Yes, excellent. Any question here? Is it June يا رودينا ولا جان?
June, miss.
Is it June? طب okay. So yeah, Alishba, it is June 2021, as Rodina says. June 2021. Type, okay. Number 2, this question is about the reactions of 3 compounds with the formula C6H12O. The compounds are cyclohexanol, Z-hex-3-ene-1-ol, and 1-methylcyclopentanol. Give a chemical test to show the presence of the OH group in all 3 compounds, including the expected result. Minna?
Add drops of PCl5.
Add PCl5, excellent.
It will give off misty fumes.
Excellent. Gives misty fumes of HCl, of course. Misty fumes of HCl. Now, they want us only to test the presence of alcohol by only 1 experiment. But what else? I'm just, as I told you, I'm revising with you. What other reagent can be added to show that we have an alcohol?
A carboxylic acid and sulfuric, yeah, carboxylic acid, and then it will form an ester.
Yes, excellent. You can say so. Of course, we can add, as Miral said, we can add a carboxylic acid, and since these are alcohols, they will form an ester, and you will determine the presence of the ester from its smell. You say that a fruity smell compound is formed. Yes, and what other? There's another also chemical test that we can do. Yes, excellent, Miral.
Sodium mess.
Yes, excellent, Yemen. We can add sodium metal, or we can add magnesium metal, a metal that is higher in the reactivity series than hydrogen. So we get, what do we get, Yemenna, here?
Fizzing.
Yes, excellent. We get bubbles or effervescence of hydrogen gas, of a gas, which is the hydrogen gas. We either get fizzing or bubbles of a colorless gas, which is hydrogen, because this hydrogen is going to be substituted by the sodium metal or by the magnesium metal, whatever metal you add, and you will get a colorless gas, which is hydrogen. Yes, excellent all. Now, number B, it says, give a chemical test to show the presence of a carbon-carbon double bond in Z-hex-3-ene-1-ol, including the expected result, Ya Omar.
Add the bromine water.
Yes, excellent. Add bromine water, and what is the?
It turns from reddish brown to colorless.
Yes, excellent. Turns from either you say reddish brown or you say orange or reddish brown to colorless. If you even write brown only, it's okay. If you write orange, if you write reddish brown, all these are correct. Yes, excellent, Ya Omar. The test you have given in BI is repeated with 1-methyl cyclopentanol. Give the observation for this test with 1-methyl cyclopentanol. Miral, what happens if you add the bromine water to 1-methyl cyclopentanol?
Sorry, the solution stays orange because there isn't a carbon-to-carbon double bond.
Yes, excellent. The solution here stays orange as there is no C double bond C. Yes, excellent. So no color change. Excellent, Miral. Yes, Asma, excellent. Okay, Rodina. Separate samples of each of these compounds are warmed with acidified potassium dichromate 6. We are going to add acidified potassium dichromate 6. Complete the table to give the color change observed, if any.
The first one is orange to green.
The first one is orange to green. Yes.
This one is also orange to green.
We hear also orange to green.
And the last one, I think, is no reaction because it's...
Yes. No observation or no reaction or no change. Excellent. That's because, as Rodina says, this is a tertiary alcohol. And of course, we know that tertiary alcohols, this is a tertiary alcohol where the carbon that is bonded to the OH is bonded to 3 other carbon atoms. And of course, no oxidation will take place. But this is a primary alcohol and this is a secondary alcohol. Yes, excellent, Rodina. Okay, Alishba, spectroscopy provides information about the structure of these 3 compounds. Let me draw the 3 compounds in front of us, Hannah. Okay. Spectroscopy provides information about the structure of these 3 compounds. Some infrared data is given in the table. Identify the wave number range and the bond responsible for one peak, which you would expect to see in the infrared spectra of all the 3 compounds, Ya Alishba.
Okay, miss, 1 second. It would be the 3750 to 3200.
Excellent. 3000 750 to 3,200 centimeter minus 1, corresponding to what?
The OH stretching in alcohols.
Yes, excellent, corresponding to the OH stretching vibrations. Stretching vibration. Or يعني corresponding to the OH bond. يعني you can say so, or you can say stretching vibration. Okay. Abdurrahman, identify the wave number range and the bond responsible for one peak, which you would expect to see in the infrared spectra of only one of the compounds.
1669 to 1645,
Yes, excellent.
which corresponds to C double bond C in alkenes.
Yes, excellent. Corresponds to the C double bond C. Yes, excellent. Of course, in the second compound. Yes. Give a reason why there is a peak at M over Z equal 100 in the mass spectra of all the three compounds, ya Abdurrahman.
Because all three compounds have the same molecular mass, so 100 is the
Excellent.
molecular mass peak.
Yes, excellent. So all the compounds, all the three compounds have a molecular mass equal to 100, which shows the molecular ion peak at 100, at M over Z equal 100. Yes, excellent. Do you have any question here? Type, okay. Asma, fragmentation of 1-methyl cyclopentanol. This one, let me erase this. Fragmentation of 1-methyl cyclopentanol results in a significant peak at M over Z equal 85. Suggests structures of the two species formed when one bond in 1-methyl cyclopentanol breaks, resulting in the peak M over Z equal 85.
So there's a free radical substitution here, right?
No, this is fragmentation in the mass spectrometer, not free radical substitution. This is the fragmentation that takes place in the mass spectrometer. M over Z means that we are dealing with mass spectrometer, isn't it?
Yeah.
Okay. You know what's the fragmentation of 1-methyl cyclopentanol?
No.
You forgot?
Yes.
Type. Okay. We said that whenever a compound, and whether it is an element or a compound, an organic compound, is introduced inside the mass spectrometer, what happens? The compound is going to be subjected or bombarded with highly energetic beam of electrons, isn't it? Coming from an electron gun. You remember? You remember this? This is in unit 1.
Yeah, I do remember that.
Okay, so what happens when the electrons bombard the organic molecule? It's going to eject an electron outside this molecule and it forms a positive ion, isn't it? And then this positive ion is going to be subjected also to the highly energetic beam of electrons. And so it's going to be fragmented. What do we mean by fragmented? It means it's going to be broken. So it breaks to different fragments. One of them should be in the form of an ion, and the other should be in the form of a free radical. So either we get this part as a positive ion and the other as a free radical, or the opposite, that this would be the free radical and this would be the positive ion. And of course, in the mass spectrometer, only positive ions are seen. These ions give peaks in the mass spectrometer. Okay, so if you draw the relative abundance or the percentage relative abundance against the mass over Z charge, the mass over Z ratio, what do we get? We get peaks, isn't it? Every peak corresponds to one of these positive ions that are broken from the initial compound that we started with. You remember it now, Yasma? So you
Yes.
have to break the molecule at many
So
parts
a
and
methyl
see
group
which
is
one of them
broken,
will give
right?
this. Yes,
A methyl group.
yes, excellent.
Okay.
So this means that the methyl group is broken. So
Yes.
if the methyl group is broken, yes, excellent, yes, what is going to be left? We have 1, 2, 3, 4, 5 carbon atoms. How many hydrogens, Yasma?
What is that? It's an alcohol, so 1 minute. I'll have 12.
Okay, this is 1. Okay, here we don't have a hydrogen because this carbon already was bonded to
I'll be 11, sorry, because cyclic.
So 1, 2, 3, 4, 5, 6, 7, 11, 12. Either you say 11OH or 12OH, 12O, isn't it?
Yeah.
Here you don't have any hydrogen. So 2, 4, 6, 8. Why is it 12? No. It's 2, 4, 6, 8, and then 9. So it's C5H9O. Okay. So if
Okay.
you, of course, you have to write it in the form of an ion. You have to write it like this and put a positive ion to show that this is the structure of the ion that is fragmented. Now let's calculate the molecular mass of the C5H9O. So C5 makes 60 and 9 and 16. So this will be 85. So yes, this is the
And the other
first species.
is
Yes,
CH3, a methyl group, right?
CH3 free radical, because one of them is broken in the form of a positive ion and the other will be in the form of a free radical. Where are these? No, this was broken, Alishba. This was broken. This is not the molecular ion peak. They didn't say that this is the molecular ion peak. The molecular ion peak is the last peak from which we can get the molecular mass of the compound, isn't it? But this is a fragmented part. They said fragmentation. Understand me? This is not the molecular ion peak type. Okay, yes, we broke it. Thank you, Alishba. Rodaina, yes? Yes, this is the sorry, I wrote only CH3 is OH, not CH3. Yes. No, because maybe you are calculating the 3 hydrogens here as well, isn't it, Rodina? We broke this part. You understand? This is fragmentation. It means that we broke the methyl group. And so here you have only a carbon bonded to an OH. A carbon bonded to an OH in the form of a positive ion. Where are the 11? Where are the 11 hydrogens? Would you please point to me here? Make annotation and point to me.
Miss, I think it's because I drew it wrong. I drew it like the displayed formula that we usually draw out. Like I separated the cyclic. I didn't do skeletal. I did the normal displayed formula.
Okay, even if you draw the displayed formula, it will be here a carbon that is bonded to an OH, isn't it? And this carbon is bonded to a CH2, isn't it? CH2. So we only have 9 hydrogens. 2, 4, 6, 8, 9.
Miss, it's because I forgot the general formula for cycloalkanes.
It doesn't matter. Even if you forgot the general formula, you draw it. You draw it in this way. Okay.
Okay, Miss, thank you.
You're welcome. Okay, would you please all, as you see, there is a question about ions, another question about titration, a third question about organic. So always the exam come in the same way, more or less in the same way. Of course, there was a type of exams at which they bring you, I don't know if we are going to see it here or not, but if we don't see it here, inshallah, we will see it in a different exam. Okay, would you please all read the experiment? Okay, Minna, state the color change observed at the end point of the titration.
Is it yellow to orange?
Yes, excellent. From yellow to orange. From yellow to orange. Yes. Some of the results are shown. Final, okay. Final burette reading and initial burette reading and the titer. So would you please, Yamena, complete the table?
For the first one, it will be 45.1.
45.1, okay. For this one,
21.80.
yes, excellent. Give a reason why the first titer should not be used to calculate the mean titer.
It's not concordant.
Yes, excellent. It is not concordant with the other values or with the other titers. So you see the questions are repeated. Yani we did this more than once. They usually ask you about this rough titration, why we do not use it in calculation. At once we say that it is not concordant. We have to write this expression. It is not concordant. Or you can say it is not within the plus minus 0.2 centimeter cube within within the range of the other titers. It should be plus minus 0.2, or we say concordant type. Okay. Excellent, Minna. Miral, calculate the number of moles of hydrochloric acid in the mean titer.
So the mean titer is 21.85 centimeters cubed.
Yes,
So you
this
do
was 21.8, and this is 21.85, and this is 21.9. So what was the mean titer, Yamiral?
21.85 centimeters
Yes,
cubed.
excellent.
And then you
21.85. Yes.
You
And
divide to get it in decimeters, and then you multiply it by 0.2 because that's a concentration.
so
So
the
you
number of
can-
moles of HCl, as Miral said, is equal to 21.85 divided by 1,000 times 0.2. So what did you get, Yamiral?
4.37 times 10 to the power of minus 3.
Yes, excellent. Moles. Okay. The equation for the reaction in the titration is, they give you the equation for the reaction. And even if they don't give you the equation, you have to write it to find out the number of moles of the other reagent or the other reactant. So calculate the concentration of barium hydroxide in grams per decimeter cube, ya Omar, giving your answer to an appropriate number of significant figures.
We will calculate the moles of barium hydroxide.
Yes, excellent. So the number of moles of barium hydroxide equal.
So 0.00.
Okay, what are you going to do, Yani, to get it?
I'll divide it by 2.
Yes, excellent. As the mole ratio here is 1 to 2, so we divide the number of moles of HCl by 2, so we get 0.00 what, ya Omar?
21.
218. 5, isn't it?
5, yes.
Yes, okay, moles. Yes, and then?
Then we calculate the mass of barium hydroxide in 10 centimeter cube, which is moles times the MR, which is 0.00218.
Yes, you are going to get, we have to get the concentration, isn't it? If you, okay, tell me what you are
Yes, I
going
will
to
get
do.
them. I'll get the mass in 10 centimeter cube. Then,
Yes, okay, yes.
do cross
Understood.
multiplication to get that.
Yes, okay, I understood what you did. You are going to do, and I'm going to, of course, explain another method. So Omar said, excellent, that the number of moles equal mass over the molar mass, from which the mass equal the number of moles times the molar mass of barium hydroxide. What did you get for the molar mass of barium hydroxide?
0.0.
No, what is the molar mass of barium hydroxide? You did it at once يعني على الكالكوليتر؟
Yes, miss.
طيب
No,
okay.
damn.
So يعني I got this 1.71. Yes, so what would be
0.3,
the
miss.
0.3? So here
Yes.
there is a 0.3 for the barium. Type, okay.
Then we'll get 0
Yes.
374
374 3
grams.
point grams. Type, okay, yes. So as Omar said, this mass is present in
10
they
centimeter
want
cube.
in 10 centimeter cube. Excellent. So what will be the mass? This is the 0.374 is present in 10 centimeter cube. So what will be the mass per thousand?
We'll do cross multiplication to get it.
Yes, which means that the mass equal 37, sorry, the concentration equal 37.4 grams per mole, per decimeter cube. Grams per decimeter cube. Yes, excellent, يا عمر. Yes, also there was another يعني an alternative method. Of course, what Omar did is excellent. And there's an alternative method that we say that this is the number of moles. Sorry, this is the number of moles. So we say that the concentration equal the number of moles divided by the volume. And so the number of moles, which is 0.02185, divided by the volume, which is 10 over 1,000. And we get the concentration in mole per decimeter cube. And then we multiply it by the molecular mass of the compound to get the grams per decimeter cube. So either you do this or you do that, both are correct. Any question? You have any question here? Type. Okay, let's go to the next question. Rodina, solid samples of soluble barium compounds, such as barium oxide, are toxic by inhalation due to the presence of barium ions. Give a safety precaution that should be used to minimize this risk when adding barium oxide to water.
Conduct it in a fume cupboard.
Excellent. Use it in a fuming cupboard, or conducted as Rodina said, in a fuming cupboard. Barium also forms a peroxide. A bottle of barium peroxide has the hazard symbol, this one. Give the meaning of this symbol, ya Rodina.
It's flammable.
No, this is not flammable. Flammable if you do not have this circle in the middle. Flammable, then you have this. Yani you see this without the circle inside. This is flammable.
Oxidizing agent, right?
Yes,
It's
excellent. This is an oxidizing agent. Yes, yes, ma'am. This is an oxidizing agent. Yes, excellent. Okay. Number 4, this is the organic preparation. So number 4, please all of you read it. Yes, Alishba, suggest why the percentage yield of 1-bromobutane might be lower if the cold water bath was not used in step 1.
Because the reaction would be vigorous, so it might splash out.
It might splash out, or what else?
Um,
The reactant, our reactant is butanol, isn't it? And we know that alcohols
oh,
are
it's
volatile.
flammable as well.
No, we don't say flammable, but we may say that the reactant or the product may escape. Okay,
Okay.
it may escape, or it can, as you said, it may splash outside, as you said at the beginning. Yes, Alishba, excellent. So whenever they, as I told you last time, whenever they say that the reaction took place in cold water bath or placed over ice or whatever, we have to say that when they ask us, why do we place this over cold water bath or ice or whatever they ask you, then you have to say that the reaction is either we say vigorous or we say exothermic, always. And if you say it explodes, this will be wrong. Either you say it is vigorous or you say that it is an exothermic reaction. So why do we put it there in this water bath or cold water bath? To reduce the evaporation, because the reaction is exothermic. So to reduce the evaporation of the alcohol, because we start here with an alcohol. And we know that alcohols are volatile liquids. So in order to reduce the escape or to reduce the evaporation of the alcohol, or else we can also say to reduce the evaporation of the product, which is the bromobutane, or either we say evaporation or we say escape, or maybe as Alishba said, to reduce the splashing outside the conical flask. All these are correct. Okay. So we say either to reduce the evaporation of the butanol or the evaporation of the bromobutane, or we say to reduce the splashing of the liquid outside the conical flask, or the escape of these reactants or products. Right. Okay, excellent, Alishba. Abdurrahman, state what must be added to the mixture in the flask before heating in step 2.
Anti-bumping granules.
Yes, excellent. Anti-bumping granules. And in a lot of exams, they will ask you what is the effect of these anti-bumping granules. We say here anti-bumping granules. Sometimes they will ask you what is the use of using these anti-bumping granules. What do we say, Abdurrahman?
It promotes even boiling.
Excellent. It promotes even boiling, or we say to prevent the formation of large bubbles, or to say to assist the formation of small bubbles. But of course, what Abdurrahman said is excellent. It promotes even boiling. Yes, but of course, we can say the others to prevent the formation of large bubbles or to assist the formation of small bubbles. Okay, excellent. Draw a label diagram, Ya Abdurrahman, of the apparatus that you would use to heat the mixture under reflux.
So we will draw a pear-shaped flask.
We draw a pear-shaped flask. Okay.
With a condenser above it.
Yes, condenser vertical.
Yes, vertically.
The condenser should be placed vertically over the flask, over the pear-shaped flask. So here Of course, this should be, we should write it in the, we should draw it in this way. And then what are you going to do next, Ya Abdurrahman?
Water in from below and water out from above.
Yes, water in and water out.
And heat from below the
Yes,
flask.
heat. Excellent. And here we have to write the reaction mixture that we are going to heat under a flux. Yes, excellent.
And anti-bombing granules.
Well, anti-bumping granules. Excellent. Okay. Excellent, Ya Abdurrahman. Do you have any question here? طيب, okay. Sorry. Asma.
Yes.
Purification of the product occurs in steps 3 to 6. State why sodium hydrogen carbonate solution is added to step 4. State why sodium hydrogen carbonate solution is added in step 4.
Can we go back to step 4?
Yes, yes.
Okay. Okay, so it's to neutralize the sulfuric acid.
Yes, to neutralize any excess sulfuric acid present, because part of the sulfuric acid made the reaction with the sodium bromide. You remember from unit 2, we know that when sodium bromide reacts with sulfuric acid, it produces the hydrogen bromide, and the hydrogen bromide reacts with the butanol to produce the bromobutane. So here, excellent, Ya Asma, that the sodium hydrogen carbonate neutralizes the excess sodium, the excess sulfuric acid. Excellent. Asma, addition of sodium hydrogen carbonate solution in step 4 causes vigorous effervescence. Explain how the problem associated with step 4 should be dealt with.
Okay, I can't really get to the problem, but I know that the bubbling problem can be solved by moving the lid or whatever we're covering the apparatus with.
Yes, we have to open or remove the stopper, isn't it?
Yes.
They said here, add a suitable quantity of butane 1-ol and sodium bromide solution to a round bottom flask. هنا Abdurrahman, we have to draw here a round bottom flask. Of course, يعني, it can also be a pear shape, but because they stated here that's a round bottom flask, so draw it a round bottom flask. Okay, because they stated here it is a round bottom flask. But if they do not state anything, so you can draw the pear-shaped flask. And then heat the mixture in the flask under a flux for 24 minutes. Rearrange the apparatus for هنا بقى they rearrange the apparatus for distillation and distill the reaction mixture, isn't it? So when they said that, here they said addition of sodium hydrogen carbonate solution in step 4 causes vigorous effervescence. And
Okay,
explain.
but okay,
Yes.
I kind of have an idea. So
Yes.
vigorous effervescence causes pressure.
Yes,
right?
excellent.
So we'll remove the lid to just decrease the pressure a bit.
Yes, excellent. So of course they are doing distillation, and we said that when they do distillation, they are going to rearrange the apparatus so that the condenser is tilted in this direction, and this condenser is going to be connected to, the receiving adapter. And we said that the receiving adapter should have an opening here, and then this is going to be connected to the collecting vessel, isn't it? Here we should always have this receiving adapter having an opening, and that's because, as Asma said now, the addition of sodium hydrogen carbonate, when it forms vigorous effervescence with the reaction mixture, this means that there will be a build-up of pressure. So we say as a build-up of pressure is formed within the system, is formed within the system. So either, because here we were placing this in steel head that is connected to the thermometer, isn't it? And here we have our flask that we are making the distillation in. So either we remove the stopper here, either we remove this stopper to allow for the pressure to be, to go outside, or else we place here an adapter that is open so that this opening would reduce the pressure that is built up within the system. So they said here, explain how the problem associated with step 4 should be dealt with. So we will say that a build-up of pressure is formed within the system. So either we remove the stopper here, either we remove the stopper to reduce this pressure built up, or else we connect the condenser to a receiving adapter that has an opening to also reduce the pressure built up in the system. Okay. Of course, you are not going to draw anything. I'm just drawing in order to explain for you what happens. Do you have any question? Type. Minna, give the purpose of the anhydrous calcium chloride used in step 5.
Miss, can you go to step 5? To remove water?
Yes, it's a drying agent. always in the preparation of organic compounds, we have to add at the end a drying agent. The drying agents could be anhydrous, any one of the following: anhydrous sodium sulfate, or anhydrous calcium sulfate, or anhydrous calcium chloride, or magnesium sulfate. All these are drying agents. So we use it as a drying agent. We use the anhydrous calcium chloride as a drying agent in order to remove water from the organic liquid. And we said that sometimes they will ask you, I don't know if there is a question afterwards concerning this part or not, but sometimes they will ask you, how do you know? How do you know that now the organic liquid is free from water? How do you know that the organic compound is free from water? It is dehydrated, it is dried, it is dried completely. So we say that the solution turns from cloudy to clear. You say the solution because when the organic liquid has water, it is not completely dried. You will see that it has a cloudy appearance. But when you add the anhydrous sodium sulfate and you shake the liquid, it turns clear, from cloudy to clear. And also, if you look at the anhydrous calcium chloride, the anhydrous will always be in the form of a powder, and when it absorbs the water from the liquid, it turns to crystals. It will form crystals. Okay. Okay, thank you, Aminna. Yes, this is what I was talking about. State how the appearance in the organic liquid would change in step 5, Yamiral.
The solution would go from cloudy to clear.
Yes, excellent. Miral, for the final distillation in step 6, a thermometer with a scale giving readings to the nearest 1 degree Celsius was provided. Give a suitable temperature range for the collection of the pure 1-bromobutane. I'm going to go upward, but please read the question first.
Okay, doctor, can you go up now?
Yes.
Please. From 100 to 104
Yes,
degrees.
excellent. From 100 to 104, you can write so. You can write so, excellent, Yamiral, because we choose always 2 degrees Celsius below and 2 degrees Celsius above the boiling temperature of whatever they are collecting. Or you can say 101 to 100 and, for example, 101, so 103, you can say so also. You can choose numbers around the boiling temperature of the bromo butane, either 1 degree Celsius below and 1 degree Celsius above, or you choose 2 and 2. So these are correct. Degrees Celsius, of course. Yes, Miral, would you please also be with us in the next question as well? Addition of sodium hydrogen carbonate solution in step 4 causes vigorous no. A student was asked to prepare 20 centimeter cube of 1 bromobutane using the procedure described. The student knew that the percentage yield would be less than 100%. Give one possible reason for the yield being less than 100%.
Transfer losses between the apparatus.
Yes, excellent. Okay, so there will be transfer losses. What do you mean by transfer losses? It means that when you prepared the compound and while you are transferring it from one vessel to the other, you can lose part of it in the vessel that you transfer the liquid from to the other. Some of the liquid would adhere to the sides of the beaker or would adhere to the side of the apparatus you were using. So when they say give one possible reason for the yield being less than 100%, you say, as Miral said, incomplete transfer or transfer losses from one apparatus to the next. Yes, excellent. Okay, Omar, after some research, the student decided to use 21 gram of butane 1-ol to prepare 20 centimeter cube of 1 bromobutane. Calculate the percentage yield that the student expected to obtain. I'm going to scroll up, but please, read the question. Okay, Omar.
So first we're gonna calculate the number of moles of butane 1-ol,
Yes, excellent. The number of moles of butane 1-ol,
which is 21 over 74,
over 74, yes,
equal to 0.2838.
38. Okay.
So the number of moles of bromobutane is the same since it had the same molar ratio.
Number of moles of C4HBr H9Br is equal to the same number of moles. Yes, excellent.
Then we're gonna multiply by the MR, which is 137.
Yes, to get the mass,
Yes.
equal the number of moles times the MR. So 0.2838 times 137,
Equal to 38.88.
38.88 grams. Time. Okay.
So now we're gonna calculate the volume,
Yes, excellent.
which is mass over density,
Density
is
equal mass over volume. So volume equal mass over density equal,
so 38.88 divided by
yes,
1.27
excellent.
equal to 30.6.
to 30,
30.6.
30.6 centimeter cube. Okay.
So the percentage yield is theoretical over actual, which
The
is
actual over the theoretical.
actual over the theoretical. So 20
Yes.
divided by 30.6
Yes.
times 100.
Yes. What did you get?
65.3.
Yes. Excellent. Excellent, Yom. Yes, Alishba. Excellent, Yom. Can you explain what you've done so far? I don't understand. Okay. Type. In any reaction, whenever you prepare a compound from another, you have to find out first the number of moles of the reacting reagent, isn't it? Of the reactant. You have to get the number of moles of the reactant. From where do we get the number of moles, the Alishba? From here, they give us the mass of the butane 1-ol that they started with. So we divide the mass by the molecular mass. Here, they give us the molecular mass of the butane 1-ol to get the number of moles. Okay. And from the mole ratio between the reactant and the product, the mole ratio is 1:1, which means that this number of moles is also equal to the number of moles of the bromobutane. Understand till here?
Yes.
Okay. Now, from this number of moles, you can calculate the mass of the bromobutane obtained. Because whenever they give you a volume or a mass in the problem, this is the actual mass or the actual volume. Because we know that the percentage yield equal the actual yield divided by the theoretical yield times 100. The actual yield is always the one that is given in the problem. So here, when they told you that 20 centimeter cube of 1 bromobutane is obtained, this means that this is the actual yield. You have to find out the theoretical. And since they gave you the actual yield in centimeter cube, then the theoretical also should be in the form of a centimeter cube, in the form of a volume. So we got the mass of the bromobutane. It is equal to the number of moles times the molar mass that they gave us here to be 137. So Omar multiplied the number of moles of the bromobutane times its molar mass, and we got the mass. Now we want to change this mass to the volume so that the actual volume, so that the actual yield and the obtained and the theoretical yield should both be in the form of centimeter cube. So we want to change this mass to volume. So how can we do that? We have the rule that the density equal mass over volume, which means that the volume equal the mass over the density. We got the mass here, 38.88. And we have the density. They gave us the density of the 1 bromobutane to be 1.27. So if we divide them, we get 30.6 centimeter cube. So this is the theoretical yield, the calculated or theoretical yield. So to get the percentage yield, we divide the actual yield they gave us in the problem divided by the theoretical times 100, and we get the percentage. Of course, they are not going to tell you that this is the actual yield, but whatever they give you in the problem, this means that this is the actual yield. They said 20 centimeter cube are obtained. They said, after some research, the student decided to use 21 gram of butane 1-ol to prepare 20 centimeter cube. So to prepare this volume, this means that this is the actual yield that the student wants to get. Understand it now?
Yes, miss, thank you.
You're welcome. Okay, so this exam is finished. Let's see something. I don't know, there were a certain type of questions I didn't meet till now. 1 minute to see if it's present in Jan 2021 or not. Yes, this is the one I was. No, we solved a lot, Asma, about answer P, but I wanted this type of questions because we didn't solve from them till now. So this is Jan 2021. We solved a lot, Asma, about if you hear the because you are not attending our lessons lately, so you can hear the records. You will find that we solved many questions about the enthalpy. Okay. This type of questions that I wanted to solve with you, a student was provided with 5 test tubes labeled A, B, C, D, and E, each containing a colorless aqueous solution. The 5 solutions were known to be barium chloride, nitric acid, potassium bromide, silver nitrate, sodium carbonate. The student carried out a series of tests to identify which test tube contained which solution. Okay, you can read the question until I write the solutions. Okay, Minna, let's go step by step. 1 minute, because I didn't read yet. I didn't read yet. Okay, now these are the 5 solutions that we want to find out which solution corresponds to the test. The student carried out a series of tests to identify which test tube containing which solution. The student tested each solution using universal indicator paper. Only solution A turned paper red. Identify solution A. Yes, Manna, that's excellent. Okay, Abdurrahman.
Nitric acid.
Yes, excellent. So A is nitric acid. Okay. Is it solution A? Type, okay. Abdurrahman, the student mixed 1 centimeter cube of solution A, which now we know that it is nitric acid, separately with 1 centimeter cube of each of the other solutions. There was no change for 3 of the mixtures, but effervescence was observed when solution A was added to C. Identify solution C.
Sodium carbonate.
Yes, excellent. C will be sodium carbonate because only carbonate would give effervescence with the acids, but the others will not give anything. Yes, excellent, Abdurrahman. Alishba, write an ionic equation for the reaction between solution A and solution C. State symbols are not required. This is what I wrote you before. Yes, تفضل. Yes, Alishba. Yes, Alishba. Yes. Yes, excellent. Yes. Excellent. Yes, excellent, but there is something missing. If you don't put it, you will lose a mark. Yes, excellent, Alishba. That's the correct ionic equation that Alishba wrote. As I told you, they usually bring such equations in the Unit 3 exam. Okay, of course, this is simple, but you have to know it. Yes, excellent. Okay. Asma, the student then mixed 1 centimeter cube samples of the remaining solutions as shown in table. B and D, no change. B and E, cream, precipitate. D and E, white precipitate. Identify the 3 remaining solutions. Which one, Yamin? Yes, excellent. Hey, Asma, the cream precipitate and the white precipitate, these are of white. Of what, sorry?
Hi, did you ask me? I didn't hear.
Excuse me?
Did you ask me?
Yes, I asked. I was
That
waiting for you.
lagged for a minute. I'm sorry.
Time, okay. So
Yep,
what do you think? What is solution B? What is solution D? And what is solution E?
Give me a minute to think.
Yes. And even if you are not the one to be asked, yani, you have to think about it by yourself. I mean that all of you should think about all the questions, not only the one I asked.
So when silver nitrate is added to barium chloride, it forms a cream precipitate.
With what, Asma? With
So B and E. One is barium chloride and one is silver nitrate.
which one of them is the silver nitrate and which one of them is the barium chloride?
Okay, when silver nitrate is added to potassium bromide gives a
So
white
solution, no, the
So
white
solution
precipitate.
B
No,
is
1 minute, 1 minute, please.
potassium.
Yes, B is potassium. So you said that when, what gives the white precipitate and what gives the creamy precipitate?
The cream precipitate is barium.
No, barium does not react with silver nitrate. You mean barium chloride?
Yeah, barium chloride.
Okay, this means that the chloride, when reacts with silver nitrate, gives a creamy precipitate? No,
Not sure.
no, it's the chloride, when it reacts with silver nitrate, gives the white precipitate of silver chloride, okay? They are, yani, as we go down the group, the color gets darker, isn't it? We usually say so. As we go down a group, the color
white
change.
cream, then yellow.
Yes, so the chloride is the one that before the bromide and the bromide before the iodide, isn't it? So this
Yes.
with silver ion would give the creamy precipitate of silver bromide. This is creamy. And the iodide with the silver ion would give us the silver iodide, which is yellow. Okay, so which
Yeah.
one of them is the silver nitrate now?
Silver nitrate is E.
Yes, excellent. And what will be B?
B is potassium bromide.
Excellent. And what is D?
It's barium chloride.
Yes, excellent. So this is B, this is D, and this is E. Type, okay. 3 of the cations of the compounds. So we don't want these. 3 of the cations in the compounds, Yamina, in A can be identified using flame tests. Complete the table. The cation formula and the flame color. Yani, let's return back كده. Which one of these would form a flame color and what is the flame color?
Potassium,
Yes.
it will form lilac flame.
Potassium ion would form a lilac flame. Yes.
And sodium plus,
Yes.
yellow flame.
Excellent.
And barium,
Excellent.
apple green.
Excellent. Yes. Any question? Okay. Miral, would you please, all of you, of course, read the question, and Miral will start solving.
So that all the solution is transferred into the volumetric flask.
Give a possible reason why any solution remaining in the beaker is washed into the volumetric flask before making up to the mark. Yes. Would you please repeat what you said, Yamiral?
So that all the solution is transferred into the volumetric flask and there isn't any left behind in the beaker.
Yes, excellent. So that all the acid solution, which is the ethane dioic acid, should be transferred to the volumetric flask and nothing is left behind. Yes, excellent. Of course, I would like to remind you of what is a standard solution. Do you know, Yamiral, what is a standard solution?
Yes, doctor.
Yes, would you please give me a definition of the standard solution?
It's when you make a solution using solid acid salt, and then you fill up the volumetric flask to 250 centimeters cubed, and you can calculate the concentration of it.
Yes, so we say that the standard solution, didn't I ask you about the standard solution? Yes, a standard solution is a solution, standard solution, the definition of the standard solution. It is a solution whose concentration is accurately known. This is the definition of the standard solution. The standard solution is a solution whose concentration is accurately known. It means that its concentration is known and it does not change. And we can know it exactly, what it is. Now, what you said is how to prepare the standard solution, isn't it? It's how to prepare it. But when they ask you about the definition of a standard solution, you have to say that it is a solution whose concentration is accurately known. And we have taken some conditions that must be present in order for a compound. When we use it, we can prepare a standard solution. Do you remember, Ya Abdurrahman, what are these conditions? We say that we have something called a primary standard substance. And if we use this primary standard substance, we are going to prepare the standard solution. Do you remember what are the conditions for the primary standard substance? Because you could be asked about such a thing. Do you remember them, Abdurrahman?
It should be a solid.
Excellent. It should be a solid. I'm going through the Mirodina now. Yes, it should be a solid. Number 2.
It should have a high molar mass.
Excellent. Has a high molecular mass.
Doesn't absorb CO2 from the air.
Bravo, Ali. Does not absorb CO2 from the air, or does not absorb carbon dioxide or moisture, isn't it? Or moisture from the air. As you see here, they said sodium hydroxide reacts with carbon dioxide in the air and should be standardized. What do you mean should be standardized? It means that when you prepare a solution of sodium hydroxide, you cannot determine its concentration accurately. I will repeat. They say that sodium hydroxide reacts with carbon dioxide in the air and should be standardized before use. It means that when we prepare a solution by the method that Miral told us about, we weigh a certain mass of sodium hydroxide and we dissolve it in water and then transfer it into the volumetric flask and complete to the mark, yes, we prepared a solution of sodium hydroxide, but we cannot determine its concentration accurately. Why? Because sodium hydroxide reacts with carbon dioxide in the air and forms sodium carbonate. And so one of the main conditions of a primary standard substance that is used to prepare standard solution, that it does not absorb carbon dioxide or moisture, because sometimes some of the solids absorb moisture. So when you weigh them, you weigh the solid plus water inside it. So you cannot get the concentration that you want. So it does not absorb carbon dioxide or moisture from the air. Yes, ya Abdurrahman, do you remember the fourth condition?
Should have a high melting point.
Okay, but يعني there are others that يعني are more important.
I don't remember.
Dissolves easily in water, isn't it? Dissolves easily in water, because when we want to prepare it, it dissolves easily in water, isn't it? So these are the four main factors or conditions that must be present in a primary standard substance. Of course, that it does not. Okay. Yeah, but it should be a solid. It has a high molar mass, does not absorb carbon dioxide or moisture from the air, and dissolves easily in water. So if you look at HCl, we cannot prepare a standard solution from HCl, because HCl at its standard physical state is in the form of a gas. It is called hydrogen chloride gas. And when we dissolve it in water, we get hydrogen chloride solution. So it's not a solid, we cannot use it. Also, although sodium hydroxide is a solid, yet we cannot use it as a primary standard substance. We cannot prepare a standard solution out of it because it absorbs or reacts with carbon dioxide in the air. Okay. Sulfuric acid is also not considered a primary standard substance because it's a liquid. In its standard physical state, it is a liquid. Okay, I'm just revising with you. Of course, they didn't ask you about such a thing, but they can ask you in a different exam. And of course, as Miral said, when we have the yes, excellent, Abdurrahman. Yani before we proceed, I would like to thank you really, because you know these things. So here, when you want to prepare the standard solution, we weigh the solid that we want to prepare the standard solution with. We add a small amount of water. Of course, we have to use either we call it deionized water or we say distilled water. Both are correct. And we stir the solution, and then we transfer the solution to the 250 volumetric flask that we want to prepare. And it will, for example, we will get the solution in this part, but there is a mark here. And then after we transfer, of course, as we said, that we have to transfer the solution using a funnel, so as not to drop any drop outside the volumetric flask. All the solution must be poured here inside the volumetric flask. If you do not put the funnel, so maybe drops of the solution would spill outside the volumetric flask. Okay, so after we place the solution here, after being dissolved and place it in the volumetric flask, we have to wash, or we say rinse, the sides of the beaker. Rinse the sides of the beaker by distilled water, by distilled or deionized water, and transfer the washings to the volumetric flask. So we rinse. What do we mean by rinse? We said that we place water at the sides of the beaker several times, not only once. We rinse means that we wash the sides of the beaker several times with distilled water, and we transfer the washings to the volumetric flask. And after we do that, we complete to the mark by distilled water. We complete to the mark by distilled water. And then the next step is to invert after طبعا, of course, when we place the lid of the volumetric flask and invert it several times, and invert it up and down several times to ensure complete mixing of the whole solution. Okay, do you have any question here? Because in some exams, they would ask you to prepare a standard solution. Yes, Miral, you wanted to ask something?
Yeah, doctor, could you explain why absorbing carbon dioxide affects it? Because I don't understand that part.
Okay. Now, if you want, did you write, before I go, did you write these things? Because if I go to the whiteboard, this will be erased.
Yes, doctor, I wrote them.
Time. Okay. So now, if you want to prepare sodium hydroxide, what do you do? For example, if you say that I want to prepare 0.1 mole per decimeter cube sodium hydroxide in a 250 centimeter cube volumetric flask. What do you do? At the beginning, you do your calculations in order to see how many grams of sodium hydroxide you want to weigh, isn't it? So you say that I want to prepare 0.1 mole per decimeter cube in 250. So the number of moles equal concentration times volume. So the concentration equal 0.1 times the volume, which is 250 divided by 1,000. So for example, we want to weigh how many grams? 0.025 grams or what? Yeah, sorry, this is moles. This is moles, isn't it? So the number of moles equal concentration times volume is 0.025 moles. Now the next step, you say that the number of moles equal the mass over the molar mass, from which the mass that we want to measure is the number of moles times the molar mass of sodium hydroxide, which is 40, and you get the mass in grams. Now, when you weigh this mass, now what is this mass, for example, Yani? It is 0.025, yes?
I got 1 gram.
Okay, 1 gram. Okay, so you have to weigh 1 gram of sodium hydroxide and place it in the volumetric flask, isn't it? Now, what happens if sodium hydroxide absorbs carbon dioxide from the air? Will it remain sodium hydroxide? No. Part of it will change to sodium carbonate. Part of it will change to sodium carbonate. And the rest of it, yes, is in the form, still in the form of sodium hydroxide, because the carbon dioxide we know in the air does not have a high percentage. It's only 0.04% of the air composition. But part of the sodium hydroxide, even if it is a small part, will react with the carbon dioxide and form sodium carbonate. So the mass you take of 1 gram is not sodium hydroxide. It is sodium hydroxide plus the sodium carbonate that is present in the bottle of the sodium hydroxide. You understand me?
Yes, doctor, thank you.
So now when you say that I prepared sodium hydroxide with this concentration, this is not true. This is not accurate. Why? Because it is less than 0.1. It's not 0.1. Because some of the solid is not in the form of sodium hydroxide, but is in the form of sodium carbonate. Okay, understand me all? Do you have any question? Calculate the concentration of this standard solution of ethane dioic acid. So now they said that sodium hydroxide is not a primary standard, and so it should be standardized. What do you mean by standardized? It means that we have to okay, Rodina, but after we finish this, please remind me afterwards, okay? So here, when they say it should be standardized, what do you mean by that? It means that you're welcome, dear, but please remind me, because I'm going to forget. What do you mean by standardized? It means that after we prepare the sodium hydroxide, we have to titrate it against an acid because sodium hydroxide is a base. We have to titrate it against an acid which is primary standard. It is an acid that can be prepared with accurate known concentration. So here, standardized means that we are going to titrate the sodium hydroxide with the ethane dioic acid, which is a primary standard substance. And when we prepare it, it forms a standard solution. So they say calculate the concentration of this standard solution of ethane dioic acid. So ethane dioic acid is a standard solution. So Miral, how can we calculate its concentration?
First you find the moles, so 2.4 over 90, which is 0.027.
Over what? 90 you said, or what?
Yes, 90.
90. So ethane dioic acid has this structure. So 2 carbons and 4 oxygens and 2 hydrogens. So as Miral said, it's 90. So what did you get here, Miral?
0.027.
Okay. Okay, and then?
And the concentration is moles over volume. So you do
Excellent.
0.027 over 250 divided by 1,000.
Yes, excellent.
I got 0.11 to 2 decimal places.
0.11 mole per decimeter cube.
Yes, doctor.
Time. Okay. Thank you so much, Miral. Okay. Yes, they gave us the molar mass, and we didn't have to calculate it. And they want you to give to an appropriate number of significant figures. Okay. Wasn't any number here more than 0.11?
I think everything was to 2 significant figures, so that's what I did.
Okay. Okay. Omar, a different standard solution. Okay, I'd like Rodina to answer this because, Omar, I think you answered 2 questions now, having calculations, isn't it? Does this contain any calculations? I don't know. Okay, let's read the question. A different standard solution of ethane dioic acid is used to determine the concentration of a sodium hydroxide solution J. A burette is rinsed with deionized water. The burette is then rinsed with 0.09 mole per decimeter cube ethane dioic acid and filled with this acid solution. A pipette is used to transfer 25 centimeter cube portion of solution J to conical flasks. The portions are titrated with ethane dioic acid solution using phenolphthalein indicator. Okay, Omar, explain why the burette is rinsed with ethane dioic acid solution in step 2.
To remove excess water.
Excellent. To remove any water present, not excess, any water present. We want to remove it in order not to dilute our solution. Okay, so here the burette must be rinsed with ethane dioic acid. After it is rinsed with water, it should be rinsed with the ethane dioic acid to remove any water present so as not to dilute the acid. We don't want it to have a diluted concentration. Yes, excellent. The diagram shows how the student read the filled pipette in step 3. Identify the 2 mistakes the student made. Yes, Yama.
The meniscus should be in the pipette marker.
Yes, excellent. The meniscus should be touching the mark, the pipette mark. The meniscus, or the bottom of the meniscus should touch the pipette mark, or should be on the pipette mark. Yes, excellent. What else?
Yeah, and the eye should be in the same level of the.
Yes, excellent. The
bottom
eye
of the
should
meniscus.
be on the same level of the meniscus. Yes, excellent. So these are the 2 mistakes. Excellent, Omar.
Doctor, I don't get the
Yes.
first.
The first one, when
Yes.
you take the volume of anything, of course, if you put water or any solution in a cylinder that is narrow, you will find that the liquid takes this form, isn't it? If you place water or if you place any solution in a cylinder, you will find that the solution takes this form. It's not leveled like this, isn't it, Yasma?
Yes.
So when you take the volume, you should take care that the meniscus, the lower bottom of the meniscus, is on the mark of the pipette, or if you are measuring a volume using a measuring cylinder or in a burette, always take the bottom of the meniscus on the level of the mark of the pipette or the burette or the cylinder. Okay?
Thank you.
You're welcome. But in an experiment, in one of the exams, they said that a student made like this. At the beginning, he took the volume at the top part of this curved shape of the solution. He took this as an initial reading, and in the final reading, he did the same. He took the volume so that the mark be at the upper top of the solution. So they asked the students, will this affect the volume of the titer? No, it does not affect the volume of the titer, because he did a mistake, yes, but he did it twice. He did it when he read the initial reading, and he did it when he read the final reading. So the error will cancel. The error here will cancel because he did the same error in both readings. But if he was taking only one reading, yes, it would affect. And if he was taking only one reading, so if he take it in this way, so the mark of the pipette be here, and the meniscus was away from the mark, then this volume is wrong. So if he is measuring a solution using a pipette to put it in the conical flask, of course, this will be wrong, and it will give him wrong calculations and wrong volumes. But if he is using a burette, and we know that in a burette, we measure an initial reading and a final reading. So if he make the same mistake in measuring the initial and the final reading, so the volume of the titer will not be affected because he did the same mistake twice. So one of them canceled the other. Understand what I mean? Okay. Time. Yes, excellent, ya Omar. Rodaina. The student completely emptied the pipette for each transfer in step 3. Explain the effect on the titer of completely emptying the pipette rather than leaving a small amount of solution in the tip.
One second, Miss.
Yes, please.
There will be too much of the solution, so your titer value should increase, right?
Yes, excellent. Bravo, Aliki. Excellent. What do you mean by this? You remember that I told you when we use a pipette, the pipette is constructed so that after we transfer the solution in the pipette, there will be a drop of solution at the tip of the pipette, isn't it? It is constructed in this way so that after we remove all the liquid in the pipette and we transfer it to the conical flask, there should be a drop of the solution present here must be present on the tip of the pipette. We don't have to blow here. We don't have to blow in the pipette so that this drop falls and falls down with the other solution. We have to leave it. So he is saying now that the student completely emptied the pipette. It means that the student blew in the pipette here so that this drop falls in the solution. And of course, this is wrong because, as Rodaina said, now the volume of sodium hydroxide will increase. And this means that the titer value also will increase. Any question? Yes, excellent, Rodina. Now, Rodina, state the color change in the conical flask at the end point. Would you like me to scroll up to see the indicator used?
Please. It's phenolphthalein, I think.
It was
Phenolphthalein.
phenolphthalein. Yes, excellent. Excellent. So what will be the color change?
To colorless.
From pink
Pink
to
to-
colorless. Yes, excellent. From pink to colorless. Yes, excellent. Abdurrahman, the titration results are shown. Complete the table and calculate the mean titer.
So for the first titration, it will be 25.05,
Yes,
and for the second it will be 24.2,
0.6 or 0.1.
0.6, sorry.
Yes,
And for the third one, it will be 24.5.
okay. So which values are concordant and we should use them to get the mean titer?
2 and 3.
Yes, excellent. We are going to use 2 and 3 because the difference in the titer value is plus minus 0.2. And of course, we are going to neglect this one. And so the mean titer will be?
24.55.
The volume will be 24.55. Yes, excellent. So Abdurrahman, calculate the concentration of sodium hydroxide solution in mole per decimeter cube. And the equation for the titration is this equation. We want the concentration of sodium hydroxide.
So firstly, we get the number of moles of ethanediolic acid,
Yes, excellent. The number of moles of the acid.
which is the concentration, which is 0.05.
Yes, 0.05 or
9,
0.09.
sorry, 9.
Yes, 0.09 times.
Times 24.55 over 1,000.
Yes, excellent.
The answer is 2.2095 multiplied 10 power negative 3.
Yes, excellent.
Miss, can I see the equation?
Yes,
So to get the number of moles of sodium hydroxide, we multiply by 2, since
excellent.
it's a 2 to 1 molar ratio.
Yes, excellent. The molar ratio 1 to 2. So 2 times 2.2095 times 10 to the power minus 3. And this will be
4.419 multiplied 10 power negative 3.
yes, excellent.
So now to get the concentration of sodium hydroxide,
Yes,
we'll say the number of moles, which is 4.419 multiplied 10 power negative 3.
4.419 times 10 to the power negative 3 divided by,
The volume, which is 25, divide 1,000.
yes, excellent.
The answer is 0.17.
0.17.
7.
Another 7.
Yes.
Okay, mole per decimeter cube. Yes. Okay, excellent. Do you have any question, any one of you? Type, okay. Thank you, Abdurrahman. Number 3, Alishba, would you please read the question?
Is to avoid suckback.
Excuse me, I'm just reading the question, 1 minute. A student heated a sample of group 2 carbonate until no more gas was produced. The equation for the decomposition is the metal carbonate gives metal oxide plus carbon dioxide. They placed the metal carbonate here and heated, and they connected the test tube to another tube that lie below a measuring cylinder placed in water. Give a reason why the delivery tube must be removed from the water bath before removing the test tube from the heat source. Yes, Alishba?
To avoid suckback.
Yes, excellent. Okay, Rudaina, you remember you asked me when do we say to prevent the suckback? So here they said give a reason why the delivery tube must be removed from the water. The delivery tube must be removed from the water bath before removing the test tube from the source of the heat source. This is to prevent the suckback of the solution, to prevent the suckback of the water or the liquid here. Okay, the results of the experiments are shown. This is the volume of carbon dioxide that is collected here, of course. It's 95. The mass of test tube plus carbonate was 21.69. The mass of test tube alone was 21.36. So the mass of the carbonate is 0.33. Alish, by using the results of experiment, identify the group 2 metal, and they gave you that the molar volume of the gas at room temperature and pressure is 24.
Miss, can I see the equation, please?
Yes. The equation says that the metal carbonate decomposes to give metal oxide plus carbon dioxide. Yes.
You can work out the moles of carbon dioxide.
Yes, excellent. We find out. They want you to find out the metal, isn't it? So even if you are given the mass of the metal carbonate, you cannot determine its molar mass because the metal is unknown. So the only way that you find out the number of moles of carbon dioxide, as Alishba said. So what will it be, Alishba?
It will be 95
Yes.
divided by 24,000,
Yes, excellent.
which gives 3.958.
Okay, why don't you do the opposite, Yani? Because we usually do the volume in decimeter cube divided by, so this is 95 divided by 1,000 divided by 24. So what is the number of moles? Okay, it's the same. Sorry, it's the same.
Okay.
Okay.
3.958 times 10 to the minus 3.
Times 10 to the power minus 3.
Yes.
Okay, Tayo.
And then from the equation, we know it's the 1-to-1 ratio.
Excellent.
So the moles of the metal carbonate is also the same.
Yes, excellent.
So then we will use to work out the MR.
Yes.
We do the mass over the moles.
We get the MR equal the mass divided by the number of moles. Yes.
And the mass of the carbonate is 0.33 divided by the 3.958 times 10 to the minus 3.
0.33 divided by 3.958 times 10 to the power minus 3.
One second. But this gives 83.375.
Okay.
And then you minus the MR of the carbonate,
Yes, excellent.
which is 12 plus 16 times 3,
Yes.
which is 60. So That's 23.3.
23.375 or 23.4. Yes, gram per mole. Okay.
Which is magnesium.
Yes, excellent. So the metal of group 2 is magnesium. Yes, excellent. Excellent, Ali. Do you have any question here? Right, okay. Using the results of experiment, identify, خلاص, we did this. The student suggested that the experiment could be made more accurate by increasing the mass of the carbonate from 0.33 grams to 1 gram. No change to the size of the apparatus or the method of measurement of the gas produced would be made. So Asma,
Just give me a minute.
the sodium is, I think, Rodina, I don't have a, because they said that this is a group 2. Let me get a periodic table. They said that it is a group 2 metal, isn't it?
Yeah, Miss, I just saw that part. I didn't realize they said group 2. I got
Type,
confused.
okay.
I'm all
Type.
for some.
So now it's okay with you? Type.
Yeah. Thank you.
Type. Okay, thank you so much. Now, Asma, they said that no change to the size of the apparatus or the method of the measurement of the gas produced would be made. Comment on this suggestion.
Okay, so it would increase accuracy as more gas would be given off.
Yes. First, we have here 2 marks, isn't it?
Yes.
So as you said that it will increase the accuracy. Why will it increase the accuracy?
As the mass of carbonate isn't the limiting reactant anymore.
No, yani why, when we have now, when we get an increase in the mass of the carbonate from 0.33 to 1, then you said that this will increase the accuracy. Yes, this is correct. Why will it increase the accuracy? It reduces what?
Reduce uncertainty.
Yes, excellent. It reduces the percentage uncertainty, because we said that the more we have of the mass, the more we have of volume, this will reduce the percentage uncertainty.
Can I
Isn't it?
talk about limiting reactant if the question was 3 marks?
It's 2 marks. Yes, if it was in 3 marks. Tab, okay, yes, you can say so. Tamam. So here, what will happen, as you said, Ba'a, they said, or the method of measurement of the gas produced, they said this will be more accurate and it will increase by increasing the mass of the carbonate. We said that this will reduce the percentage uncertainty, and also so the volume of the gas given off, as you said before, would be greater. Yes, excellent. Okay, this is an enthalpy, so would you please, Asma, also solve it? The enthalpy change for the thermal decomposition of a carbonate is difficult to measure directly. An example of Hess's law cycle to determine it indirectly is the metal carbonate gives metal oxide plus carbon dioxide. If we react the metal carbonate with HCl and the metal oxide by HCl, we get metal chloride plus water plus carbon dioxide. In an experiment to determine the delta H1, this one, 0.05 moles of the metal carbonate was placed in a 100 centimeter cube beaker. 60 centimeter cube of 2 mole per decimeter cube hydrochloric acid and excess was added and the mixture stirred. The maximum temperature rise was 6 degrees Celsius. Heat capacity of the solution is this one. Calculate the enthalpy change for the reaction between the metal carbonate and hydrochloric acid, Asma. Include
Okay,
a sign in your answer.
Okay, so the enthalpy change is negative change in negative Q over N. First, we'll get the Q, which is mass multiplied by heat capacity multiplied by change in temperature. So we'll multiply mass, which is 60, multiplied by 4.18, multiplied by 6. Just a minute, I'll
Yes,
calculate
1
it.
minute in an experiment. Okay, yes, so 60 times 4.18 times 6.
which will give us 1504.8 joules.
Like this?
Yes.
Okay.
Now we'll get the moles.
Yes.
Yeah, okay, 1 minute. Moles would be 0.05.
Yes,
So
because the
number-
HCl is excess. So we have to take the moles of the metal carbonate. So delta H will be 1 equal to minus.
okay, so 1.5 1.505
Yes.
divided by 0.05.
Yes.
I
Excellent.
converted the Q to kilojoules because they
Yes.
asked in joules.
Mm.
Just a minute to calculate it. How many significant figures do I need?
Here you should have, if you have here 60 centimeter cube, but you have here 4.18. So you will get it in 3 significant figures.
3, okay. It's 30.1.
Okay.
Negative 30.1 kilojoule per mole.
Okay. Yes, excellent, Yasma. Of course, you have to revise what I told you, the previous recordings, because there were different types of questions on enthalpy change. Okay.
Yeah, I will. I just couldn't for the past 2 days because I had 2 exams back to back.
Type. Okay. God be with you. Using your answer to CI, calculate the enthalpy change delta HR for the thermal decomposition of group 2 carbonate in kilojoules per mole and include a sign. Now this is minus 30.1. So what is the delta HR?
It would be negative 30.1 plus 150,
Yes, excellent.
which would be 120.9.
120.9.
No, it's 119.9. Yeah, sorry.
So it's 120
Yes.
kilojoules per mole. Yes, excellent. Any question here? Type. Okay, now, of course, because maybe our time is running,